online ATAL online FDP on recent trends in high performance computing using artificial intelligence, organized by Department of Computer Science Engineering, Bonu Venkatachalma Institute of Technology and Science, Amlapuram. Today, first session, that is 7th session, will be hosted by Dr. S.S.S.N. Usha Devi Madam, Assistant Professor of JNTU Kakinada, an N-panel HPC expert by AICTE. Then second session, 8th session will host by Mr. Venkata Gurram, an industry expert from overseas, USA. First, all the participants to please be joined as session time 6 o'clock is reached. I welcome participants and resource persons. Good evening, madam.
Sir, good evening, sir.
Very good evening, madam. Welcome to today's session on CUDA programming. On behalf of Department of Computer Science and ATAL FDP organization, we welcome Dr. S.S.N. Usha Devi Madam, Assistant Professor of JNTU Kakinada, and N-panel HPC expert by AICTE. Already first session was handled in the inauguration. After inauguration, I request Mrs. Usha Devi Madam to start today's session on CUDA programming. Participants are joining, madam. You please start, madam. The session time is on.
Okay, sir. Okay, sir. Done.
Thank you. One minute.
Is the screen is visible, sir?
Visible, madam. Visible.
Okay. Good evening to everyone. Today, in this session, I would like to share my views about CUDA programming and how these multiple cores are going to be integrated together to improve the performance of your model, that may be any AI model or ML model. Let us see the architectures first, then we go to the programming also. So I have a plan to discuss the architecture as well as programming in this session. So these are the contents. So need of processors, introduction to GPUs. So GPU architecture And there are a lot of terminology we need to know actually before going to implement the CUDA programs and all. So types of GPUs, CUDA programming basics, and then some sample CUDA programs. So before going to that, we just look at what are the various changes that happened from 1980 to 2020. So in everywhere, that means in the hardware architecture. So how we can observe the changes. Just let us go through it. So here in this diagram, you can see it's a single CPU with a memory, and it's a sequential programs, megaflops. So it is going to be next shared memory, gigaflops, and next multiple nodes, teraflops. So if you observe here, that means here shared, the second one is a shared, third one is a distributed one. Distributed memory in which each CPU has its own memory. So here, if you observe the data bit 8-bit to 16-bit to 64-bit, so it got increased. Data bit means, so how many bits we can transfer for a particular time, in particular unit time. So that means it is updated from 8 to 16 and then 16 to 64. So it is increasing. And number of cores. So initially we have i4 systems, i5 systems, now i7, i10 also some people are using, right? So instructions per cycle. So I hope you already aware of the instruction per cycle means, right? How many instructions per a cycle they are going to be executed. So these are also increased. And also clock rate. The processor clock rate also gone increased. So these are the multiple changes that are observed in this period. So in major thing is here I would like to talk about the flops here, mega flops, gigaflops, and teraflops. I mentioned flops, right? So actually the flops are going to be calculated using this formula, number of operations into clock speed into number of cores operations per cycle. That means you can observe if anyone is increasing in the numerator components, number of operations, clock speed, and number of cores operations per cycle per execution time. Okay, so if the clock speed increase, automatically the flops, no, number of floating point operations per second is going to increase. So these are the things that are going to affect the flops, the speed of the system. Previously we have seen that the speed of the system is going to be measured in terms of floating point operations per second, right? So that is a formula for flops. Next, graphics processing unit, GPU. So why we need a GPU actually? So we already aware of central processing unit. CPU is already we are using, right? So why we need a GPU? The GPU is also an electronic circuit. It is not something different from CPU. I will show the architecture of the GPU also. So GPU is an electronic circuit that is utilized for improving the performance, the speed of the system. In terms of speed only we can improve. Okay. That means whenever we observe, repetitively we are doing certain tasks. So that can be parallelized and that can be run by GPU to improve the performance of the system. So these devices are mostly going to be in video cards, system boards. So nowadays we are able to see a Dell laptop, gaming laptops with the GPUs inbuilt. So that is also there. And because of these GPUs, we can reduce the time. So of course, we need to incur certain costs for these GPUs, but we can reduce the time. Whenever we feel that the time is very important, we need to get the output in a short span. For example, so a bigger storm is going to hit our city. So then immediately we need to generate the signal. In such a case, if you run using the large data using the CPU system, then there will be a lot of, I can say that loss is going to happen. Okay. But if we incur certain cost for this GPU, it is going to do the work for us, and it's going to give the generate the attention in short span, so that we can alert all the people. So that will be the better model. Okay. So nowadays, in hazard detection or hazard management, so for such kind of things, we are going for the GPU also, for getting the result in a faster manner. So it is also useful for the future technologies, AI, blockchain, ML. We will also see why this GPU is useful for ML and AI. In next few slides, I'm going to share my thoughts about it. From 2010 onwards, the GPU got the popularity because of this tensor cores. Let us see this thing, tensor cores. Just you remember this one, and in next slide I am going to explain what is this tensor core. So why it gained the popularity because of this tensor core operations. So GPU is also having a faster RAM, okay, which we usually term it as a GDDR, okay, graphics double data rate synchronous dynamic random access memory. Okay, so those are called GDDRs. So we have two versions of GDDRs, GDDR6X, GDDR6. So GDDR6X is somewhat faster and consumes less power for the computation. But the problem is it is faster, so it already consumes that power to do the operation faster. Okay, that will have less transfer rate, data transfer rate, but sorry, less power for data transfer rate. But the point is, as it is faster, it is computing. It is sorry for this, for its computation, it requires power again. So it is going to be balanced one, but we will get the result faster. So here where there's one more term you can see, IGPU, integrated GPUs. So which are just next to CPU slot, there will be one GPU kept on the board, and you just remember this PCA. We will see the PCA also. That's the interface connect. Okay, through interface connect only it is going to CPU and GPU communication is going to happen. So these are somewhat a new terminology, right? So let us see one by one. We'll go. Okay. So GPU and tensor. Already we talk about this one, right? From 2010 onwards, the GPU is getting popularity because of the tensor operations. So what is tensor? In generally, when we say tensor, just visualize an array. 2D tensor means two-dimensional array. So when you visualize two-dimensional array, what is it? It is going to hold the data. So that means tensor is a data structure that holds some data. Suppose if you consider any application, image processing application, so we just, whether it is a 3D image or 4D image, whatever it may be, we consider that as one array only. So that's the thing, right? We consider that one as an array. So array computations are very much important for AML. Of course, for A, we generally go for algorithms only. For ML and DL, deep learning models, array computations are very much important because they are the basic operations in ML and DL, machine learning and deep learning. So here, so GPU has the power of optimizing those tensor operations because it mainly focuses on the vector additions, vector multiplications, vector operations. So tensors are the core data structures in machine learning, and here these tensor operations can be computed with the GPU because GPU deals with vector operations. So that is why it got a popularity from that year onwards. So nowadays, the people are started using these GPUs for transformers. Let us see how they are going to use. So tensor operations on GPUs. These are some sample operations, matrix multiplication. So core of the deep learning model. That's without any matrix multiplication, we cannot perform any learning process. For example, if you consider any neural network, what is the output of a neural network? The simply input array into weights, and that is going to be submitted to the activation function, and it is going to perform certain manipulation on the matrix, and again it's going to produce certain data. So again this data will be multiplied with weight matrix, that's an array, and again that is going to be multiplied with, that's not array, that may be any dimension, so that is an array, and again it is going to be in the second layer, it is going to be multiplied with some other weight matrix. So totally matrix multiplication is the basic operation in any neural network. So it's a core of deep learning model. So convolutions used in CNN. So for convolution operation, so receptor field, receptor to get the receptor field and to identify the feature map, definitely we require tensor operation. So that's it. That can be done by the GPU in a faster way, because GPU are meant for performing these vector operations. So activation functions, ReLU sigmoid softmax functions, batch normalization and attention mechanism in transformers. So I want to give you one brief idea about these transformers. So transformers, they are going to done the work in parallel with some attention mechanism. Batch normalization is an optimization technique that is going to improve the performance of the model. So for this kind of transformers, again, it requires tensor operation. So that is why here GPU is going to be very helpful. So for this, I can tell one example, BET model, BET language model. So which is a transformer that uses these tensor operations. Next is CPU versus GPU, how they appears to be. So actually in this diagram, we can observe the common aspects. Memory, both have memory, but the GPU is having global memory and shared memory. So here ALU register file, everything is common, and control unit also PC, IR, instruction register, program counter, these two are common. I connected to IO device, that is also common, right? But here major thing is memory is different for GPU. The major important thing is this is going to use a different kind of memory to speed its operations. Okay, and here CPU primarily performs serial tasks and controls the working of the system in a serial fashion only. Even though we have a lot of branching statements, already we have discussed this, right? We are having a lot of branching statement, the operation is a serial only. And next, accelerators are parallel operation devices made for a single task to be performed repeatedly at a rapid pace. So here we would like to perform certain tasks repeatedly. Only those tasks can be parallelized and that can be assigned to the GPU for the purpose of work. Suppose if you don't have any parallel task in your program or in your application, we don't have any kind of is there any message for me? It's not for me, right?
No, madam, no, madam.
Okay. Okay. I'm not looking at chat, but something is appearing continuously, so that's why. Okay.
Will intimate, sir. No,
Okay.
madam, no.
So here, suppose if there is no parallel operation in your application or in your program, then there is no chance of applying this kind of HPC or assigning the task to the GPU. Unnecessarily, we cannot assign any task to GPU. If something can be parallelized, then only we need to opt for GPU. So number of transistors also, arithmetic logical unit, control unit, cache memory. So here CPU, of course, the ALU arithmetic logical unit, more transistors are going to be there, and control unit more for the CPU, and cache is also more. So here for GPU, it is not required, so it is less. So it is designed like that. So CPU is going to have a small number of large cores, and you can observe in the diagram also. So this one, small number of large cores, because it may be I4, I5. Those are the number of cores. And GPU accelerator. Whenever I say accelerator, means it is going to improve the performance. Accelerates the performance. So that's accelerator. GPU accelerator optimizes for parallel task. Here, large number of small cores. You can observe this green color indicates large number of small cores. So low latency, there will be certain delay in data transferring and all. But here we use GDDRs, right? So that is why it's not going to deal with a low latency, and it will have a high throughput. Okay, number of operations, number of input operations per second is going to be very high. And it is optimized for serial processing and optimized for parallel processing. Designed for running complex programs. Okay, designed for repetitive and complex calculations. And one thing is, for a particular application, we cannot say that GPU is going to be going to give a better solution than CPU, the normal computing. Okay, there is no such a thing. Whenever we require parallelization, whenever there is a need for parallelization, then it is better to go for GPU. That's the option. So for every application, no need to go for the GPU. So CPU is also designed to perform complex tasks, but the point is, whenever there is a repetitive task, then we need to go for GPU. Cost efficient for smaller workloads, cost efficient for bigger workloads. Next, types of GPUs. So discrete, integrated, and virtual. So these are the three common types. So discrete types. So these are called DGPUs. Okay. So they are separate from the device CPU. So that means outside of the CPU, and information is going to be transferred from CPU to GPU and so on. So they are distinct chips with connectors to separate circuit board attached to the CPU by using an express slot. So separate slot will be there. But whereas integrated, previously we have seen this kind of thing. iGPU. This is integrated GPU. So a slot will be next to CPU, and the PCI, the interface, the peripheral interface is going to take care of. It's called PCI Express. Sometimes we can see PCIe. So it represents PCI Express. So this interconnect is going to take care of, this interface is going to take care of the CPU GPU communication. Actually, so why I'm talking about the CPU GPU communication? We already have a GPU that is having high computation power, right? Why we need a CPU then? So later we're going to see, there is a question to you, and I will ask you at the end. The question is whether GPU runs without CPU. So that's the question, whether GPU runs without CPU. At the end, you need to answer this question, whether GPU runs without CPU. Okay, even though you know the answer. Okay, so I will ask at the end only. Okay, then you all can share, so that I will get a collective answer, how many people are giving the answer. So the power of, okay, now this is the thing. So this is going to have a high power, because faster rate we can transfer the data. Why we need to transfer the data from CPU to GPU? Let us see in the next slides. We are going to see that. So whenever we have gaming laptops, majorly we'll have such a kind of integrated GPUs. Within system, we can see the GPU slot. Is there any disturbance here? Am I clear to you?
Yes, madam.
Okay, thank you so much. So within the laptop, we can see, suppose if that is a gaming laptop, we can see the GPU is integrated with the CPU. Okay, maximum for the video gaming and all, we will have such a kind of integrated GPUs. So virtual GPUs, that means the GPU is located somewhere. Same capabilities as discrete or integrated GPUs, but without hardware. We don't have any hardware. We just interconnect with the GPU and we do our work. So that is also we can see. They are simpler and cheaper means, easy to maintain means we need to purchase that GPU for a certain amount of time by explaining what is the workload and how many number of days you are going to work for it. For example, Google Colab is offering one GPU node. In this session, I would like to share that also, how to set the GPU and how to use the Google Colab GPU. Okay. So next, there is one more term you can see, NPU versus GPU NPU. And what is this NPU? This is neural processing unit. And this term is different from GPU or both are same. Let us see, they are both complementary systems, main center that complementary to CPU. The fundamental difference between these two is the chip design architecture, and the purpose is also different. So NPU is mainly focused on data flow and memory hierarchy for better processing of AI workloads in real time. But in case of architecture, they both go for parallel processing. But NPUs are purpose built for machine learning and AI. So this is a specialized computing unit. So why they came into the picture now? Because already they are decade old, but nobody knows actually this and what is this NPU. We always hear the word GPU, CUDA programming, but we are never aware of this kind of NPU. But normally we are able to see, because the reason is the AI applications are growing very fast, and came into our lives. So nowadays everybody using the generative AI models, they require a lot of computation power. The data flow techniques are very important. So generative AI, whereas generative AI directly deals with data, right? In case of any other model, we might give certain data and we may expect certain one output or two outputs. But here the point is, in generative AI, we will give a single statement and we are expecting multiple outputs sometimes. For example, all Apple images. Some participants, I think, please mute yourself. So if you have any queries, I will answer you at the end. Thank you. Okay. So here, in the recent advancements, we are able to see a generative AI model. If you suppose, for example, if you give one sentence, artificial intelligence definitions, then it is going to produce a lot of content. So that's generative AI. So if you want to generate images, simply Apple images, simply if you type Apple, it generates a lot of images. That means we are expecting lot of information from the existing system with a short input. So that is the generative AI models, right? How they are going to work. Transfer models. How they are going to be using the transfer models only. So because of this only, this NPUs came into the picture. How to handle the data. So here, handling the data and computation power both are very much required. So this seems to be the structure of this GPU. You can see the RAM placed here and memory controller, and then the process clusters. Here you need to understand this word, streaming multiprocessor 1, streaming multiprocessor 2. So there are many clusters here. Processor cluster 1, processor cluster 2, cluster 3, cluster 4. So clusters of processors are there. So within cluster, we have streaming multiprocessor. Within streaming multiprocessor, again, cache L1 is there. And again, we have cores, right? So just we just zoom this structure and we go one by one. Okay, so we are already we have discussed this point. I'm not going into the inner details of just GDDR, how the structure is going to happen, why it is faster than a normal RAM. So that I'm just omitting that part because I would like to more focus on this internal structure, the streaming processors and the internal parts. Okay, there are multiple things are there. So let us see that which are very much useful for programming. Of course, these are the architecture of this RAM is also required. Okay. So examples of modern GPUs, CUDA, OpenGL, SYCL. So these are the graphics processing environments we can use. Sir, is there any possibility to mute participants here because I'm getting some noise here?
Yes, madam. Suresh Garu, please mute yourself. Okay, but sorry, madam.
So these are all the architectures that are released by NVIDIA over years. So Tesla, I think you are aware of this test. Just observe this word Tesla. Later we are going to see this one, Tesla. So from 2006 to 2023. So these are various models released by NVIDIA. So now let us come to the CUDA concepts. So this CUDA is a software layer. Okay, anyhow, we observe that so GPU is useful for improving the performance of the system. We can do the programming. We can do the programming, and we can get some output in a faster way. But how to do the programming? So that depends on this CUDA. This CUDA is a standard, and it works on this NVIDIA GPU. So CUDA is a software layer. So that enables us to developers to make the programs. So a programming model that uses again C, C++ Fortran. So you can do, if you select a CUDA, you can do the programming on C language, C++ and Fortran. I will show you how we can write the programs using C. Okay. And there are APIs libraries also available. So direct control over the GPU hardware, unlike OpenCL or Vulkan. So that's the advantage of CUDA. So grid collection. So grid here in CUDA, we have this kind of terminology. In CUDA programming, we have this kind of terminology: grid, block, thread, kernel. So these are very, very important things we need to remember while doing the CUDA program. So grid, collection of blocks. Collection of blocks. And again, what is a block? Block is a group of threads executed on SM. What is SM here? This streaming multiprocessor. Streaming multiprocessor. That is SM. A smallest execution unit running on a CUDA core is a thread. Okay, I will show the structure also. So next, kernel. A kernel is what in general, what is meant by kernel? Kernel, we generally in operating system we say that it's going to interact with operating system, right? That's an important function. So kernel is a function that runs on CPU, and we need to define a kernel. Within kernel, we'll write the parallel code. So what should be run in parallel? That will be kept in the kernel. For example, we have seen previously Pragma. Within Pragma, we kept the code, right, to run it parallel. Similarly here, within this kernel function, we need to keep the code. And here we can opt either C or C++. Throughout the program, we need to maintain one language. So what is PCIe? Sometimes we say that this is PCI Express. Sometimes we will get PCIe. So Peripheral Component Interconnect Express, that is going to act as an interface between the CPU and GPU. So let us see why we need interaction between CPU and GPU. What is the purpose here? We are saying that GPU is faster and GPU can perform all the tasks. And why we need a CPU then? Let us see. It is used for data transfer between GPU and CPU, the PCIe Express. PCI Express. So, and communication with system memory, because there should be certain communication with main memory for to save the temporary operations results. Okay, and again it will bring the result, right? So initially everything is going to be saved in RAM only. So connecting multiple GPUs also, it requires PCI. So you may assume that only one GPU is going to be here, but every time it is not possible. If the system is very large and we are doing high level computations, we may use multiple GPUs, and these multiple GPUs can also be connected with PCIe. And this is the GPU hierarchy. So GPU consists of multiple streaming, multiple processors. So SMs, we generally call them as SMs. So when you are dealing with any theory part of this HPC, you will always get this kind of structure. SM will always be there. Streaming multiple processor. Within SMs, we have CUDA cores. Those are called CUDA cores. So what is CUDA? Okay, this is the abbreviation for CUDA, Compute Unified Device Architecture. Okay, within SM, we have CUDA cores. And those cores are going to execute the threads. Okay, so grouped into warps. So this warp is only meant for NVIDIA. We generally use this word for NVIDIA. Okay, so Compute Unified Device Architecture is the CUDA abbreviation. Okay, and these cores are going to execute threads. In general, we always say that cores are going to execute the threads. Okay, but how these threads are grouped into warps. Okay, so like 32 threads each. Okay, so for example, here we have NVIDIA A100 GPU configuration. So this is the name of the model A100. So total SMs are 108. That means you can imagine the size of the cluster now. So see, streaming multiprocessor 1, 2, 3, 4, 5, 6, like that. It has one cluster has 108 SMs. Suppose it has 4 clusters, 4 into 108. So CUDA cores per SM 64. So total CUDA cores are 108 SMs into 64. So this many CUDA cores are available. So recently I have seen that one Microsoft application, it's a weather forecasting application that has used 40,000 cores for its computation for the weather prediction computation. Because the whenever I say weather prediction, it is having a lot of parameter, lot of attributes, right? The humidity, pressure, and temperature, and also different kinds of condition, whether it is rainy season or winter season. Again, from country to country, it is going to change. So those situations are going to change. We have all the seasons here, so we need to include our own things here. So depending on the country, depending on the region, depending on the type of season, so everything is going to change. Geographical things should also be considered while forecasting the weather. Not only this humidity, temperature, and pressure. So let us see. There are many terms here, right? Grid, block, thread, kernel, warp. Let us start with warp. So warp is going to be group of threads. Here 32 threads together. Okay, that is called warp. Okay, so it is in parallel streaming multiprocessor in a single instruction multiple thread. This is called SMD, single instruction multiple thread manner. So warp size is always 32 threads in modern, because why we are taking warp size as 32 means in modern NVIDIA GPU the warp size is 32 only. That's why we are considering 32 threads. Execution model is going to have all the 32 threads in the warp executes the same instruction at the same time. Because we talk about this one, right? It should be the similar instruction, then only we can do the parallelism. We can apply the parallelism. That means action is same. So scheduling. Warps are scheduled and executed by warp schedulers. That means there is a designer for the scheduler. Okay. The warp size is also designed how many number of threads it can execute. And it's having a specialized scheduler. Now the people are working on different types of proposing different types of schedulers also. On HPC, it's also one kind of research area, how better we can do the scheduling, warp scheduling. Next, warp divergence. If threads in a warp take different execution paths, performance decreases due to serialization. So this is warp divergence, but it should not happen actually. So next, what is thread hierarchy in CUDA? So the thread is the smallest execution unit, right? In general, what we say, process is program under execution, right? Thread is a smallest execution unit. So warp takes this 32 threads together, and thread block is a collection of multiple warps. Now if I say this is warp, and here this is a thread block, then multiple warps will be there within this thread block. Okay, so like this, I'm not doing in a structured way, but I would like to tell that if this is thread block, okay, these are warps. Okay, so a collection of multiple warps had to be thread block. And here, where are these thread blocks actually? On a grid. And again, this grid may have multiple thread blocks. So you can observe, you can understand that first of all, we can visualize a grid now, and then within the grid, thread blocks. There will be a lot of thread blocks. Okay, here is one thread block, here is also one thread block, here also one thread block. So within this grid with a lot of thread blocks, within thread block we have warps, multiple warps. Okay, so this is 3. If a thread block has 256 threads, here's a small example. I'm not getting the cursor now. Okay, so there is a small example. If a thread block has 256 threads, it is divided into 256 by 32, because every warp can hold 32 threads, right? Can group 32 threads. So 256 by 32, so 8 warps it is going to be. So each warp contains 32 threads. Okay, each warp contains 32 threads, and a thread block contains 8 warps now. So within this, there will be, I have already drawn this many, right? So like this, I can say that 1, 2, 3, 4, 5, 6, 7, 8. Of course, it's not structured actually, but you can assume that this thread block is having 8 warps. That means it's going to deal with 256 threads, 256 parallel tasks. Whenever I say thread, means it's going to execute a small part of the process, right? So which can be done in parallel. So warp size NVIDIA is going to have a 32 threads per warp, but there is also one more company, AMD. Okay, so it says wavefronts. So they use wavefront instead of warp. The nomenclature is got changed. It is a wavefront. 64 threads per wavefront. So nomenclature changes like that from company to company, but most of us use NVIDIA models only. So that's why even if you say, if you take any other company also, maximum time we are able to see NVIDIA SMs. So that is why we can simply call them as WAPs, no issue. So now SM execution model. So we understood what is thread warp, thread block, grid, right? Now come to the SM. So each SM executes multiple thread blocks. So thread per block, an SM can handle multiple blocks simultaneously. So how much concurrency is there, you can imagine. So warp equal 32 threads. All threads in a warp executes the same type of instruction. But the point is here, SM is having certain memory hierarchy. So register, shared memory, global memory, L2 latch. So anyhow, the GPU is having different GPU support different kind of memory. It's not going to be same as this kind of thing. We have already seen shared memory and global memory in GPU structure. Okay, we are talking about that. So L2 cache will be shared across SMs. So next, streaming multiprocessor fundamental processing unit, how it is going to be done. So SM contains CUDA cores, tensor cores, warp scheduler. So all, because we understood that there are groups and how to thread groups, how to manage those threads. It is going to be done by the warp scheduler. So tensor cores, shared memory, so everything. So these are all the activities that is going to be taken care of SM. So SM contains the CUDA cores, tensor cores, warp schedulers, registers, load store units, what are the main functional units, and also the cache memory, shared memory. So this many part comes under this SM, streaming multiprocessor. So, and it is different for different GPUs. So these are Ampere. So these are different GPU configurations here. We have seen A100 NVIDIA, right? So that is 108 SM in previous example. So 108 SM, 64 CUDA cores per SM, and total number of CUDA cores is 6912. Already we have seen this example. So the shared memory per SM is 164 KB. These are fixed structures. Okay. So architecture are already predefined architectures. So already these parameters are predefined for the architectures. Similarly, we have this many GPUs, amperes, ATAL overlays, okay, for these things. Next, coming to the GPU execution, the kernel launches a grid of blocks. That means how it's going to execute the thing in parallel. So kernel is the main thing that launches a grid of blocks. So once it launches the grid of blocks, what grid contains? Grid contains blocks. Block contains again these threads, right? So each block is assigned to an SM. So SM divides a block into warps of 32 threads. That is why it is constructed in a hierarchical fashion, so that they can be parallelizable. So each CUDA core executes individual threads. So this structure we can see in the programming also. So execution of threads, block and grid. So this is the thread, is a thread, and here this thread is assigned to core. We understood that a core can execute only single thread. It's not that much high level, right? Thread is a simple part in an executable process. So core is also going to handle a single thread. So thread blocks, streaming multiprocessor. Kernel grid, complete GPU unit. So this is the kernel grid. It consists of lot of threads. Okay. This is a grid. We have seen this architecture before. Grid, and within the grid, thread block is there, and within the grid, thread block is there. Many thread blocks are there, and many thread blocks. Within thread block, we can see threads. Very simple. Threads are going to be within the thread block. All the thread blocks together, we call them as grid. Okay. So it is going to be executed by complete GPU node. Okay, you can see in reverse also. The total thing is this one. We need to compute this much data with complete GPU unit. So one thread block is handled by one streaming processor. So one thread is going to be handled by one core. So this is structure. So there are two methods of doing the parallel programming on GPU. So let us see the method 1 and method 2. The general method is very, very simple one. Just there will be there will be figures also to understand this structure. So there are 6 steps actually. The steps are like, just you imagine that there are two people who can collect the data and you can communicate the data to the respective high level person. So he is going to perform the task. Okay. And again, after computation, the second person will return the data to the first person. Okay. So like in general, in bank, somebody will approach the inquiry first. Suppose if that is inquiry or any application submission. So in the first counter, they submit the application. In second counter, the application is going to be processed and the reply will come to the first counter again. And at the first counter, the person will collect the result, right? So this is general process. The same process is going to happen here. Okay, with the same analogy. Okay. So allocate and initialize memory on host, the CPU. So then allocate the memory on device unit. So whenever I say device, that is GPU. So allocating memory, because to do the computation, first we need to initialize the value. For example, we need to do certain computation, a plus b, c is equals to a plus b. First of all, what we do in C programming, we just create int a comma b, right? So that means allocation of memory. So that is very important. So here also we need to allocate, GPU side also we need to allocate. So transfer data from, now the memory allocation happened. Now the transfer data from host memory to device memory. Host memory means CPU memory. See, like how we transfer in previous case in analogy, what happened? Disk 1 to disk 2. Okay, counter to the respective counter. The other counter 1 to counter 2. So host memory to device memory. Then in counter to the major thing is going to happen, right? In similar way here. So launching kernel device, then large number of threads are going to be executed in parallel in the device memory, device part. So that device part, after computation of the entire thing in parallel, it transfers the result to the host memory again. Okay, once it is transferred, deallocate the memory and terminate the program. So this is also important. Once it is done, once it is displayed, deallocate the memory. So that is also very, very important. Okay, allocating the memory and initializing the memory at the host, on the host as well as on the device. Then transfer the data from host to device memory. Then computation at device memory. So once it is done, it is going to return the data to the host memory. So then deallocation. So these are the 6 important steps. See those steps in this diagram also. In step 1, allocate and initialize the host memory, and then allocate the device memory at GPU side, and then copy the data from host memory to device memory. Once memory is created, there is a free space. So transfer the data to the CPU memory, GPU memory, and then here launching the kernel. because without launching kernel, nothing is going to happen, because that kernel is going to take care of this grid blocks creation. That is why launch kernel is important. We'll see how it is going to be done. The next example. So next thing is, once the GPU perform the computation unit is here. Once the GPU perform the computation, it is going to return the result to the CPU memory. Now deallocate the memories, which is not required, right? Once it is computation is done, it is displayed, deallocation. So it is not going to hold anything here. Okay, it is not meant to hold anything. Its duty is to do the computation and return the result. Once one result is returned, then no need to store any data here. So it's very simple process. So next, parallel programming workflow new method is also there. So you can do either one approach. You can follow either one approach. Allocate and initialize the host memory at same time. Launching kernel on device, then deallocate, do the computation and deallocate the memory and terminate the program. So this is going to be the magic step, because large number of threads execute in parallel on device. Let's see. So this is the thing. So you can observe there is a PCI interface here. Without this interface, this CPU memory cannot be transferred to GPU memory, or GPU memory cannot give any result to CPU memory. Okay, so this interface is very, very important. So whenever we say that we are doing the programming models in HPC, it doesn't mean that you're going to have one editor, one compiler. There are a lot of things in between. So here, launch the kernel. Let me at a time launch the kernel GPU threads to process the data, and GPU's unified memory takes care of all the transfers. So this unified memory is going to take care of all the transfers. So that's why the mutually it is going to happen. And then finally deallocate. That's it. So there is one CUDA program here. You can see the vector addition program. Okay, before going to this vector addition, I would like to show small program first. So CUDA memory hierarchy we have seen, right? Shared memory, local cache here, registers. So these are the threads available to the these are the threads that can be close to the register. Here you can see the global memory DRAM, and here thread blocks. Then here you can see the shared memory, this one. Okay, see, threads related to the same task, they can have a shared memory, but this memory should not be interrupted with this memory. So that's why they have a separate shared memories. Okay, so all the thread blocks are going to can have this global memory. So this is the structure. Just you can observe. Whenever we see the grid, so it consists of blocks. We call that one as a block, thread block as block. So block 0, 0, you can observe, this is very important. Block 0, 0, 1, 0, first column and second column, 0th row, and this is first row, 0th row, first row. So 0, 1, and 1, 1, 2, 1, and so on. So here in this case, block 1, 1. If you take the block 1, 1, what is it? What it contains here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 15. Right. So here it consists of thread 0, 0, 1, 0, 2, 0, 3, 0. That means every thread is going to be identified like this with the index. Okay. 0, 2, 1, 2 and up to 4, 2. So in this way it is going to be identified. So we call them as thread IDs. Each thread is going to have its own ID, because as per the operating system definitions, every thread is going to have its own unique ID to identify it, right? So that's why thread ID Similarly, block ID, grid ID also there. So block dimension. So can you guess what is a block dimension? Block dimension depends on the number of threads running in the thing. So here it is. What's the block dimension? So it is 1, 2, 3, 4, 5, 3 by 5. So grid dimension is number of thread blocks. Okay, 2 by 3. So number of thread blocks. Okay, in row and column. Because number of blocks present in the grid going to be the grid dimension. So you take this one as example. So suppose this is an array. So we have different types of elements here. Okay. So this is thread ID. One thread. Threads belong to the first block. Threads belong to the second block. Threads belong to the third block, and so on. So it will be like this. So here, so if we have m threads per block, unique array index for each entry is given by index equal to thread id dot x, block id dot x. See here, this is a what is it, program. Yes, it is a, what we can say, it's a predefined thing to get the block id actually in the program, CUDA program. So thread id dot x, okay, block id dot x into m. That m is a width. Here, what's the width here? As you can see that, suppose to point out this one, the thread id is 5. 0, 1, 2, 3, 4, 5. This thread id is 5. The block id is 2. Okay. So you need to count from 0 only. 0, 1, 2, third one. So it is 2. So into the width is 0 to 7. That means 8 threads are there within the block. So 8 threads are there. So here m value is 8. So 21 is the index. If you observe this one, if you start from 0, so it will be 21 please. Okay. Yes, here you can see, in this example you can see. So just observe this one. This is a sample CUDA program. So where you can display the block thread IDs. Okay. So this is the structure. Hash include stdio.h consists of the printf statement. So here I'm using C only here. So I will show you how to compile and how to run the program also. So underscore, this is underscore global. Sorry. This is a structure of the program. Underscore global underscore void print thread information. That's a method name. It's a C program. It consists of main function also. This is a, what is this? What is this? This is a GPU device code here. Okay. So that can be run in parallel. So whenever I say underscore global underscore, that means it is a kernel section. Okay. Okay, let us see that one later. Just come to the main function. Int main function. So int number of blocks equal to 2, number of threads equal to 4. So block, there are 2 blocks. So grid consists of 2 blocks. Okay, grid consists of 2 blocks. In each block, we have number of threads as 4. You can observe 4 threads. Okay, that's the point. So here, print thread info. Okay, what is this thread info? It is not any existing method. We have written the method here, print thread info. So number blocks, number thread. Okay, this should be printed. Okay, so here CUDA device synchronize means ensure all prints completed before exiting. So even the it actually it is able to print the all the statements one by one like that. But here we ensure all the prints complete before exiting. So before the end of this main function, so it should complete all the prints. Then only it should exit. That is the constraint here. CUDA device synchronize. Okay. This is a predefined function. CUDA device synchronize. So here, in this case, you can observe what is this thread info. So print thread info consists of block ID. Here we need to, you need to create a memory, right? So block ID, grid ID, thread ID. So block ID dot X. So here, whenever you call this function thread info, number of blocks comma number of threads within this angular brackets. Okay, you are calling this function with two parameters, number of blocks, number of threads. It is not any predefined function. So it is user defined function. So it passes the arguments number of blocks as 2, number of threads as 4. So 2 and 4 catched by this one, right? Okay, those are assigned to this one, block ID dot X, grid ID dot grid dimension dot X. So int thread ID dot X. Okay, so grid ID, block ID, thread ID. Okay, so here grid ID, what is a grid ID consists of? Grid ID consists of grid dimension dot X, that is 2. So block ID is this one, block ID is 4, I think, right? Block ID is the block ID X. Okay, right. So what about thread ID? So every time it is going to change, because here we have a 2 number of blocks, 4 threads, right? So every time it is going to change. I'm unable to see the output. Yes. So grid ID is 2, because we have only 2 grids. Whenever there is a number of blocks as 2, that means number of grids equal to 2. So number of threads are 4. So number of blocks are, so number of threads are 4. So 0, 1, 2, 3, 0, 1, 2, 3. So blocks are 2 only, right? 0, 1. Grid ID is 2. So by default, it is taking grid ID is 2. So just wait. Actually, I would like to show one program. Just wait. I want to show one program. Just give me 1 minute. Just connecting to it. Stop sharing. Okay. Sir, are you able to see the Google Colab here?
Yes, ma'am.
Okay. It is good. Okay. So, okay, that's the theory part I told you, but actually, see, you observe this one. So you can connect to your Google Colab account and simply change the name here. This NVCC is a compiler, C compiler actually. So whether it is present or not, just check for it. The command is not symbol NVCC. Which NVCC? Just check for the NVCC whether it is available or not. Of course, it will be available because whether it is your account or my account, the Google Colab maintains the same NVCC. So there will not be an issue for NVCC. So just to know the version of this NVCC, I have taken not NVCC. So it is going to run the thing. I hope when you are familiar with the Python programming also, you need to use exclamatory mark symbol. Okay, when you are installing something, right? So similarly here we use the not NVCC -- version. So it just displays what's the version of this NVCC. You can observe that one. And next here, now let us come. I have told you one program, right? Simply you need to write the program in the cell. While writing the program, you need to add this one. Okay, modulus operator, like percentage write file. Then it is going to write the file to the cell. So write file display, that means I have given a name for this because later I need to compile the file and run the file, right? So display device underscore info.cu. Cu is the extension of the CUDA program. So here, to understand the CUDA, so I have included the CUDA runtime.h header file also. I will show you why. So this is one program. So first I would like to tell you how to compile, how to run. So we have written the program using percentage write file, then file name.cu. So after that, you need to compile the file, right? So for the compilation, this is the command. Again, not simple, let me see. The file name.cu and then -o, output file. Okay, -o. You can give the output file name. Of course, otherwise you will get the a.out as output file, but you can give the output file name, right? So -o, output file name. I have given the same name for, you can give any name, no issue. So this is compilation. And then to run the program, we have exclamatory mark dot slash the output file. In general, in Unix environment or Linux environment, we generally do the same thing, right? Dot slash a.out is going to give the result. Similarly here, whatever the output file name is, display device information. So here we have mentioned the same thing. So it is going to display the result like this. So the above program is related to the grid dimension, block dimension. So grid dimension consists of 211 blocks. That means each block size is 211, and again block dimension, that means 211 blocks are there, and block dimension is going to have this many number of threads. Okay, so there is one more program on vector addition, actually it's related to vector addition. So okay, everything is fine. You already have certain program. Okay, that may be display device information or vector addition. I told you, right? This GPU is majorly is to perform vector operations. So whatever may be the file, first you need to check the version and just write the file and then compile the file and run the file. But before that, first point is you need to check the runtime. Okay, here you can observe this one, change runtime type. Okay, change runtime type. So click on this. I have already opted the T4 GPU here. T4 GPU means Tesla. Okay, that's why I mentioned. You remember this name, Tesla. So this version is available in Google Colab. Okay, so we have a CPU version is there. T4 GPU version. By default, it will be CPU only. You need to change to GPU. Okay, and save the setting. Okay, then you need to run the program. Okay, so actually this formula is very lengthy. I don't want to discuss here. Actually the thread ID can be computed using this formula. Okay, in general, to get a particular thread ID, I think previously we have seen, right? So in terms of, just I would like to show you how the data is going to be transferred. Here in main function, dimensionality 3, grid dimension 2, block dimension 2, comma 2. Okay, print from each thread hello grid dimension, block dimension. That means there we need to print these dimensions. Okay, So what's member dimension? Grid dimension means how many thread blocks are present. Okay. Sometimes there may be multiple dimension thread blocks. That means thread block might have 3-dimension, 4-dimension, 3-dimension also. Okay. That's why it's going to be different. Sometimes 3 parameters, sometimes 2 parameters also. Sometimes we can say 2 by 4. Sometimes we will say 2 by 4 by 3 something. Okay, this formula is used to print the thread ID. So I'm going to share it, just you try to see this one. So we can identify the thread ID based on the grid dimension, block dimension, and thread ID. Like how we have seen theoretically in a previous example. So just observe this factor addition operation. There is a one main function here. Just to know that these are host vectors. H star beam, H host. For a device, I have indicated with D. Okay. That means these are the host data I'm going to maintain, and this is for device data. So allocate memory, right? That's the first operation to be done. So allocate memory for pointer H underscore A, H underscore B, H underscore C. So here star is going to represent a pointer only. That H, sorry, it's not H star H. So H underscore A is a pointer. So allocating memory for H host vectors. Okay. So what is a vector here? Vector is nothing but just a set of values, right? Here it is a vector, just a linear vector. Okay. One dimension only. You can observe that there is only one loop to save the values. That means I'm just collecting certain set of elements and copying that into H underscore A array. Of course, the names seems to be difficult. The reason is to not to get confused. We'll take like that. Okay. Otherwise, if you can take some other element names. Okay. So initializing vector. Okay. Allocating memory. Then initializing vector H underscore A, H underscore B. Okay. After that, allocate memory on device, right? That's the second step, right? So CUDA malloc. So previously, to allocate memory for host, simply we have used an malloc. We already aware of that. For pointers, we use malloc function, calloc function, right? Similarly, we have this kind of thing. So here CUDA malloc is the method that creates memory on device. So that is why CUDA malloc void star ampersand D underscore A. So what is this D underscore A? Address of device, we need to keep the data. Okay. So we need to create that much size of the data. Okay. Void star. So here copy the data from host to device. So once it is done, we already have a data on host. What do you want to do here? I want to add A is in one array, B is one dimension array, A is one dimension array. I want to add these two and save it to C. Actually, this is the objective. So CUDA mem copy is a method. So D underscore A device memory, host memory, and what is the size? And here I need to write CUDA memory copy host to device. That argument I need to include. Okay, it's a constant that I need to include. So once it is included, then automatically H underscore A data is going to be copied into D underscore A, and H underscore B data is going to be copied into D underscore B. So that is the thing. Now the data is available at device. Okay. So define execution configuration. So threads per block is 256. That means within block we have threads per block. So within the block we have this many number of 256 number of threads. So next, blocks per grid also we need to define. So this is a formula for blocks per grid when we have n. Okay, what is n here? So n is defined in the above, I think. N is 10. That means size of vector. Okay, size of vector is 10. So that means A is of size 10, B is also of size 10. Okay, that should be given here. So this formula you need to follow for blocks per grid. Suppose if you already know this is 10, then what will be the value of this one? 10 plus 256 minus 1 divided by 256. So that can directly be written, or already we have seen how many blocks are going to be there for this many number of threads. We have already computed that theoretically. Okay, that can be directly given, or it's just a formula. So next, then what is the next step? We have copied the memory and we identified how many number of threads, how many number of blocks. Then we need to check with kernel launch. So kernel launch is important, right? So that kernel launch is this one. Instruction is this one. Vector add. We don't have any vector add predefined method. Here we have, sorry. Here we have defined the method using underscore underscore global underscore. That means it is a parallelism. It's a kernel. Okay. So now we are launching the kernel. Vector add blocks per grid, threads per block, and sending the data. Okay. So A, device data, not host data. Device A, device B, and device C, comma, how many elements we have? 10 elements, right? So that N I'm going to take. So next CUDA. So after this instruction, what happens? It's not going to be here now. CUDA, the next instruction says copy result from device to host. That means once kernel is launched, automatically this is going to be executed for multiple number of times. Okay, it is going to collect. So where to keep the result? For example, A of 0 plus A of 0, B of 0 should be kept in C of 0. A of 1 and plus B of 1 should be kept in C of 1. So that formula for that, thread ID dot x plus block ID dot x, that means it's a formula. You can directly follow this one, okay, to get that index. So next, so you can theoretically try for this thread IDs, block IDs, you will get the same 0 index, 1 index, 2 index, and so on. So every time it is going to be computed and it will give the thread ID as well as this one, as well as what is A value, what is B value, what is C value. It is going to be printed. What is a thread number. So once it is done, means the data is ready, the result is ready at device C, D underscore A, sorry, D underscore C. The result is ready at D underscore C. Now we need to copy that D underscore C to host. That's why it is CUDA memcopy device to host. Device to host. So that is why here H underscore C, D underscore C, size 10. Okay. And this is this one. Next, data copied back to CPU successfully. That means just I'm printing successfully. So we already understood that the data is available at H underscore C. Simply print the result. Okay. Then once it is done, release the memory, free memory. So all the items were freed. Then return 0. So this is the vector addition program. Similarly, there are many programs can be written, but the major thing you need to understand is initially we need to create memories. Okay. Create memory for the host, create memory for the device, then copy the data from the host to device. Device means GPU. So then launch the kernel. Once kernel launch has happened, that means you are working on the parallelism. So once it is done, you will get the result at the device parameter here, D underscore C. So that should be copied to the host underscore C, and that result can be displayed and then memory should be freed. Okay. So this is the way of doing this program. So I hope you understand how to write the program. Of course, so a lot of background work should be there, because to understand this time is not sufficient to understand each component, this grid dimension, block dimension. I have given a brief idea how to compute theoretically. So for 1 or 2 times, if you run the program, you will get to know. If you theoretically analyze, you will get to know why the ID is like this, why we got the thread ID like this, why we got the grid dimension like this. Okay, you will get to know. Just you try to practice small programs, CUDA programs, then you will get to know. So first step is set the runtime, change runtime to T4 GPU, and then just write the file, use this command %, write file, and file name.cu, then use NVCC compiler. Okay, use this command, not NVCC, and file name.cu -o, and here is this one output file, and then run the file using the output file name. Okay, simply you will get the answer. Okay, so any questions? Wait, I would like to show the one disclaimer and references also, then we can go for the question. Yes, I already asked you one question. I'm expecting answer from you. I need to show the disclaimer. Just I would like to stop present this one. Sir, I'm unable to see the control. Just can you stop this one presentation? Yes, I have stopped sharing. Yes, I have stopped sharing option. I hope this is a very simple example to you. You can practice with this case study. Are you able to see the presentation slide now?
Yes, madam. Yes, madam.
Okay.
Case study is visible.
Yes. Okay. You can start with a simple case study. Okay. Then these are the references I have used. This is the disclaimer. So most of the content I have taken from the AICTE Sankalp program, which I have attended at CDAC Pune. So then some content is taken from IBM website also. IBM website, it's very interesting actually. It's going to give a lot of details about NPU, GPU, and their architectures and all. So you can go through this. So any questions?
Okay,
Yes,
respected
I asked you.
participants, if you have any doubts regarding CUDA programming, please directly ask our resource person, Mrs. Dr. Usha Devi, madam. Please.
So one point I would like to ask you actually,
Madam.
to run the GPU, whether CPU is required. Without CPU,
Yes.
is it possible to run program?
No.
So
No from me.
previously we have seen in the example, we have seen that we are collecting the data at the CPU side and transferring the data from CPU node to device, right? Host to device. And again, the GPU is doing certain computation and collecting the data and copying the data from device to host. That means here there is a communication between CPU and GPU, right? We observed that. So maximum time in lot of applications, GPU is completely dependent upon the CPU, but there are certain specialized applications. So GPU only computation is also there, but I'm not touching that concept now. But maximum times we follow this kind of communication between CPU and GPU, and with that communication, we're going to optimize the performance of our system.
Okay, dear participants, please observe that feedback form on this session is shared only in chat box of WebEx only. Please observe and submit your feedback. Thank you very much, madam, for your a great session on this CUDA programming and hands-on. Thank you very much
Thank you, sir. Thank you.
for your support.